Let's continue with the normal stress, normal strain curve as mentioned in the previous video. Now, as you can see in the elastic region, the relationship between epsilon and sigma is linear, straight line. So if we see that relationship here, if we got horizontal one and up a number, and that property we call it E, and for one material that ratio 1E are unit 1. If we go to the normal strain 1 inch over inch, then whatever go up for stress we call it E, and that is unique for each material. And from that we can consider a Hooke law, something that you already heard in physics, but now we apply for this scenario. So let's talk about the Hooke's law that we study, for example, in spring. So within a linear portion of the elastic region, what do we have for with the Hooke law? Within a linear portion of the elastic portion of the elastic region that we saw in the normal strain curve. So within the linear portion in the elastic portion of that. So the E, as you can see, the ratio vertical sigma and horizontal 1 is normal strain, and that E, believe it or not, that equation, as you can see for that slope, E is constant for the same material, so that's sigma over epsilon. I can box that for that slope, and that we call it modulus of elasticity. So E in this case, call that E a modulus of elasticity. Also, name follow scientist called Young, so it will be the Young modulus. So that is Hooke law in here. So, and modulus of elastic is unique for each material, and as you can see, it's sigma over epsilon. Epsilon is inch over inch, sigma is KSI. So the unit of E modulus of elasticity is same as sigma. So let me give example in here in your canvas. If you go to the material properties in the back page of your covers, appendix B, in the appendix B of your textbook, you can have steel and different type of steel, and you have a modulus of elasticity. For example, for ASTM A36 steel, we have it 29, then 10 power 6 psi of the modulus of elasticity. And we also will talk about modulus of rigidity in a few minutes, and also the thermal expansion, etc. in next week. So as you can see, for every material we can have that in there. So let's get back to, so if you want to refer to that, will be appendix B in your textbook. Go back to the lesson here. So that is the Hooke law, and you know the unit, you know where to find the E, modulus of elasticity. So the next concept that we want to talking about is Poisson ratio. Imagine that if we have a material, and if you extend that material, deform that material in longitudinal axis of that body, then the lateral direction, it will be compressed, it's smaller, And that ratio, we call it Poisson ratio. It's still difficult concept. I'm going to show you the demonstration right after we talking about the Poisson ratio. So stay tuned for a few minutes and you will see that. So Poisson ratio, basically we have two assumptions. We assume the materials is homogeneous. What is homogeneous? We are going to define homogeneous. So what does that mean? It will be same material throughout, same material throughout. You may say that, oh, it applies to any body, but any material, but not, that may not be true. You can see, for example, composite body may have different type of material, but this way first we need to have the same material, steel, rubber, etc. And then the next assumption is the isotropic. And iso, when you see iso, it means something the same, equal. So what does that mean? It will be same properties in all dimension. In all direction, longitudinal direction, lateral direction, etc. in all direction. So if we have that, the nu for the Poisson ratio, that call it nu, and call it nu in Greek letter. So that nu equal to negative the strain in the lateral direction over the strains, normal strain in longitudinal axis. So let's define that. Let it mean lateral. Direction. And then the not my name, it is the longitudinal direction. So from that, we can, for different material, the nu, in this case, they have a range, and that I'm going to show here. Range of Poisson ratio nu is somewhere between 0 and half. So nu is greater than 0 and less than half. But typically, it's about quarter to 1/3. So typical values of nu in here. So nu typically greater than 1/4 and less than 1/3. And after you watching this demonstration that I'm going to show you next, you practice the worksheet 2D. But let's see, as you can see, different material. If you go to the reference data card, we for this class, go to page, go down. This page number 4, you can see the different material. For example, steel, aluminum, cast iron, wood. We have the modulus of elasticity, and we also have the Poisson ratio nu in here. For example, steel 0.3, aluminum 0.33, cast iron 0.21 and 0.33. So that, as you can see, we go back to the lesson, you see the new in that range for different material. So what I do, I'll go into demonstrate what is the Poisson ratio is about, what is the normal strain in lateral axis on lateral direction, normal strain in longitudinal direction, and you go have to practice worksheet 2D before we are talking about the actual deformation in the next. This is the demonstration of the Poisson ratio, which is defined by Nu, and that the ratio between the normal strain in lateral direction and the normal strain in longitudinal direction. And with that, as you can see, that is rubber band at the natural condition, so no deformation yet. And if I apply a load that make a deformation longitudinally, so which is horizontal with the camera here, and as you can see, let's observe the rubber band will extend the length, and at the same time you see the width of the band without and with load applied. So here it look big, you see that the width of the band, and now if I apply, it becomes smaller and smaller. So if we extend the deformation in the longitudinal axis, which is the horizontal, then the lateral axis, which is or lateral direction, which is the vertical, or the width of the rubber band, it gets smaller and smaller. And that ratio between the scaling down of the lateral deformation over the longitudinal deformation, which is the extension, and that we call it Nu, and it's negative in front of that ratio, because as you can see, the increase in the longitudinal deformation, it get the decrease in the lateral deformation.